Hi, again I'm Tom Reynolds. This is video number 3 of the correlation experiment. You recall in the last video, Bert Jones talked about the downwelling irradiance sensor. To refresh your memory, the downwelling irradiance sensor is located right there. You'll recall there were 7 little openings, and the downwelling irradiance sensor measured light at 7 wavelengths. You will also recall that it was paired with the upwelling light sensor, which is right here, which measures the light coming up in a very narrow band, and it is primarily used to look at the same kind of thing as satellite does. Also, over here, this is a CTD right here. This is conductivity, temperature, and depth. What that allows us to do is to tell exactly what the depth is at any given second. What we did is we used a sensor made by Onset Computer Corporation, and it's called a hobo pendant sensor. It looks like a pendant. It looks about like an elongated matchbook, and you can see it here basically expanded. This here is a plastic case. Inside is the electronics. Now the electronics includes a light sensor, a temperature sensor, and a battery. So on that little board, which is probably less than 1 inch by 3/4 of an inch, you've got a sensor, you've got a battery, and you've got some memory to record it. The whole thing plugs together. You can see you put this all together, and it now becomes waterproof. That sensor measures white light, and we can leave it down for a little bit over a week before we have to record the data. Well, that gives me a downwelling irradiance sensor of some sort, but it doesn't give me 7 channels. And in fact, we don't need 7 channels. We only need 3. So turning here, what we do to modify that sensor is we, in fact, use 3 sensors. One, a blue filter, where we take this blue filter, an acetate filter, we slip it in so it covers the green board, and then covers the, if you can look at it closely, that is the light sensor. So only blue light is recorded by this filter, and we do the same thing over here. We put a green filter in a 3rd hobo pendant sensor, and in this way we build a downwelling irradiance sensor that has 3 channels: blue, green, and white. The good news is this whole setup here we sell for about $300, and you recall that Professor Jones said the other one was about $9,000. Alright, so now that you understand that we're measuring light at 3 different wavelengths, now we can explain to you how the rainbow sensor works. Here is a picture of the rainbow sensor Bonaire configuration. It's a mooring. Basically, in some way we attach a mooring to the reef. Then we have a rope, about a 1/2 inch rope. Up at the 3-meter level we have Coke bottles. Apparently it's got to be Coke bottles. No other kind of bottle works. And then at the 5-meter level we have those 3 sensors, blue, green, and white, and it measures the light at this level. And at 12 meters we have another set, blue, green, and white, and at 20 meters. Same, blue, green, and white. So, what we do to figure out what the organic content of the water is we read the light levels here at 12 meters, and then we read the light here at 20 meters. And in the difference of those 8 meters, the light has gotten less. However, and this is the trick, the light gets less differently in different wavelengths. In very, very, very clear water, okay, the light at the green goes away faster than the light at the blue. Light going through water, you lose the water, you lose the light according to the rainbow. Red, orange, yellow, green, blue, violet. So red is gone within 10 meters. However, that's only in very, very clear water. If the water has a large amount of organic content, the blue will climb up and it'll be attenuated or reduced about equal to the green, and then if it gets even a little more organic content, the blue will actually be released before the green. That is what we use to measure the organic content in seawater. Recall that the rainbow sensor and the more expensive 7-channel sensor are both measuring the light coming down from the sun at a variety of wavelengths. A fluorometer works differently. This fluorometer is a 3-channel fluorometer, and one channel measures chlorophyll. That's one of the things we're looking for. One channel measures CDOM, dissolved organic material. These are the two components that we're looking for in seawater. That's what we talked about, organic material. We're talking about chlorophyll and CDOM. So what this gadget does is, first of all, this channel here, the chlorophyll channel, excites or illuminates the seawater in the ultraviolet range, but measures the fluorescence or the emissions of the light in a longer wavelength, in this case blue. And the same is true, measure CDOM, it's excited in the blue range and is measuring emissions in the red range. So it's essentially a different kind of mechanism that we're using with a rainbow sensor to determine the organic components of water. Okay, so what is the correlation experiment all about? By the way, if you have trouble reading this, you can go to www.rainbowsensor.com, go to the correlation experiment page, and you can find basically JPEGs of all these pictures. Anyhow, over here on the right, we have a rainbow sensor. We see the mooring down here, we see the Coke bottles up here, and we see 3 levels of rainbow sensors. Here is the rainbow sensor test area between 12 meters and 20 meters. Our plan is next to this rainbow sensor. As close as possible, the boat is going to drop a 20 kilogram rate right here into some place on the reef where we're not messing anything up. That weight is going to have a ring in it. The P-Bop is going to be suspended on a line, running down from the P-Bop, down through the line, over here, where a diver is going to raise and lower the P-Bop depending upon the plan. We have to do it this way because if we put a boat up in here to try to drop the P-Bop down, it'll block the rainbow sensor and will mess up the data. So, looking at how we're going to do this experiment, if we set the P-Bop at 12 meters and measure it for a while, and then set the P-Bop at 20 meters and measure it for a while, then we will be doing essentially the same kind of calculation that we are doing with the rainbow sensor array, but with a higher resolution instrument. Similarly, if we measure the organic material in here, the CDOM and the chlorophyll, with the fluorometer, and now get a measurement that's been done for years and all over the world about what the dissolved organic material is, and then we go over here and we see what the rainbow sensor says, now we can draw a correlation between the two so that we can correlate the instruments on the P-Bop with the instrument right here. That is the whole primary goal of the correlation experiment.